Well, I believe we are already live. Good morning, everyone. Good afternoon for some of you. Good night. We are kicking off the second day of activities of the second workshop on computational chemistry as a strategical tool for the development of functional materials. That is the second CompChem. And I'm very pleased to be chairing the event today. Well, my name is Rodolfo Guetza Fiorotti, and I am professor of the Organic Chemistry Department here at the Universidade Federal Fluminense. First, I would like to acknowledge the audience for attending the second day and thank all the invited speakers for the acceptance to share with us part of their work. We are very honored to have very special talks today, and I wish you all a great day of conferences and scientific talks. Today we have three very exciting talks, one in the morning and two in the afternoon, which we are going to start at around at 2 p.m. sharp. And the presentations will have around 50 minutes, and we will try to separate 10 minutes. So you can please feel free to ask your questions during and after the presentations, so the speaker will address your questions. So please feel free to ask anything you'd like to. So to begin, our first invited speaker today is Professor Trevor A. Hamlin. I'll give a brief introduction of him. He is an assistant professor with tenure at the Vrije Universiteit Amsterdam. Please correct me if I'm wrong at the pronunciation. His research group is focused on unraveling reaction mechanisms and developing unified concepts to control the reactivity and selectivity of organic, inorganic, and biochemical transformations. He is track coordinator of the Theochem group. He has more than 115 published papers and more than 1,200 citations. Now he's going to talk about understanding chemical reactivity using the activation strain model. Professor Hamlin, thank you so much again for the acceptance. We are honored to have you here with us. And please feel free to start when you're ready. The screen is yours.
Yeah, thank you very much, Rodolfo, and a big thank you to all of the organizers for the invitation to give a talk at this workshop. Before I continue, can someone confirm that you can see my screen? Is everything looking okay? Okay,
yeah,
wonderful. Yeah, so as Rodolfo says, I'm one of the PIs in the Theochem group at the VU University here in Amsterdam. And today I'll talk about understanding chemical reactivity using a method that we've developed in our group. It's called the activation strain model. So here's a nice overview. Here's the roadmap of what we will accomplish during today's talk. So we will combine two methods, the activation strain model and a state-of-the-art energy decomposition analysis. We're going to combine these to study various organic reactions. So first we'll dive into the classic Diels-Alder reaction. We'll then study the Michael addition reaction. And then we will conclude with studying the strain-promoted azide alkyne cycloaddition. Also in our group, we're very much interested in studying inorganic reactions, so metal catalyzed transformations, as well as biological reactions and DNA stability and DNA replication. However, during today's talk, I'm only going to focus on these three fundamental organic reactions. So first and foremost, let's just get all on the same page with regards to this Diels-Alder reaction. So this is a 4+2 cycloaddition that occurs between a diene and a dienophile. And they combine to form a cycloadduct. You can imagine that if you were to push the electrons around, they would go in a cyclic manner. And so this reaction is considered a paracyclic reaction. now I will talk about the activation strain model. And so when you set out to study a given reaction, oftentimes you want to develop the potential energy surface. So you start out by optimizing the reactants, you then find the products, and then you eventually find the transition state. And for the Diels-Alder reaction, this is what they look like. So here is the chemdrawl of 1,3-butadiene and of ethylene. Here are the optimized structures. They react to form the cycloadduct. And we want to know the factors that give rise to the activation barrier, this delta E double dagger. And so this exactly equals the strain plus the interaction. And putting this in terms of the Diels-Alder reaction, you can understand the strain as being the energy difference between the distorted reactants and the original reactants. What exactly do I mean? Well, over the course of the reaction, all of the terminal carbons pyramidalize. They go from sp2 to sp3. As well, we have 3 pi bonds that are transformed into 3 sigma bonds, 3 carbon-carbon single bonds. So there is a reorganization of the geometry, and that's an energetic penalty. So the energy goes up. Summing to the strain, you have a favorable interaction energy. So you can imagine that these deformed reactants begin to favorably interact. You have orbitals overlapping, you have electrostatic interactions, you have stabilizing dispersion. So the barrier equals the strain plus the interaction. So now how does that look when we are investigating 2 reactions here? So we have a black reaction and a red reaction. Well, we know from transition state theory that the rate of reaction can be related to this activation barrier. And we see that the black reaction has a lower activation barrier. So this is a faster reaction than the red one. Well, when we plot this, this is the potential energy surface, delta E. So now we're going to plot our strain and interaction along this reaction coordinate. And we get such curves like this. And in this prototypical reaction, we see that the strain curves are superimposed. So they're not really contributing to the difference in barrier height. But in this example, the interaction energy is very important. So the black interaction curve is more stabilizing than the red one. So that pulls the activation barrier down and to the left. So the transition state, the black transition state, is lower and earlier on the reaction coordinate. So in this case, the reaction is interaction controlled. Now, if you look into the literature, several people perform this analysis only at the transition states. And when they carry out this analysis, they call it the distortion interaction model. Now, I want to just mention that can contribute to some misleading conclusions, because if you were to do the analysis at the transition state alone, you would conclude that the black reaction is faster because it has a lower strain energy. But that's only because the transition state's earlier on the reaction coordinate, thus it's less deformed. So in this talk, in all of our analyses, we do this analysis along a reaction coordinate, and that can change depending on the reaction that we're studying. So we advise to pick a point on the reaction coordinate that's near the transition states, and then to do your analysis there. And if you do this, this is what we say the consistent geometry. And then you would say, Indeed, the black reaction's faster because it has a more stabilizing interaction energy. Okay, so that's the activation strain model. Next, we like to decompose that interaction energy, that stabilizing interaction energy, into 3 physically meaningful terms. First, we have the electrostatic interactions, and these are your favorable Coulombic interactions between your fragments. You can imagine that on one fragment, you have electrons, and they can favorably interact with the nuclei on the other fragment. Well, in the case of the Diels-Alder reaction, we have 2 fragments, right? We have 2 reactants, the 1,3-butadiene and your dienophile. You also have the inverse. You have the nucleus on one fragment interacting with the electrons on the other. You also have the destabilizing Coulombic repulsions, the nuclei repelling with the nuclei on the other, and the same for the electrons. You have the polyrepulsion. This is your steric repulsion. The origin of this can be found in the overlap of filled orbitals. So this is a 4-electron, 2-center repulsion. So this is proportional to the overlap squared of your filled orbitals. Lastly, you have your orbital interaction, and this is your donor acceptor, your HOMO-LUMO interactions, and this is proportional to the overlap squared over delta epsilon. So the overlap of the HOMO-LUMO divided by the energy gap. So we're going to dive into the first paper. This was published recently by our PhD student, Pascal, in collaboration with Professor Bickelhaupt and Professor Fernandez in Madrid. In this paper, we studied how Lewis acids catalyze Diels-Alder reactions. So first and foremost, this workshop is roughly focused on materials, and so the Diels-Alder reaction has been a very useful transformation for functionalizing materials. And in this case, you see that this is a Diels-Alder reaction was used to functionalize nanoparticles, and they have very interesting properties whereby if you can scratch the material, it can heal. So it can undergo a Diels-Alder reaction and then a retro-Diels-Alder reaction and heal the material. You can also mix a diene and a dienophile in the presence of a Lewis acid and give rise to stereo-specific Diels-Alder reactions that lead to chiral polymers. You can also utilize a Diels-Alder reaction for various cross-linking properties. So upon heating, you can break up your polymer, and upon cooling, you can have this healing event. So nice functionalized materials, all relying on the Diels-Alder reaction. And so if you kind of remove all of the complexity of the chemistry on the previous slide, you can arise at a very simple Diels-Alder reaction, one that occurs between isoprene and this alpha-beta unsaturated ester. So this reaction, when run at room temperature for 70 days, you obtain a mixture of the 1,3 cycloaddict and the 1,4 cycloaddict. And I believe the yield is about 50% or so. So you get a mixture of 2 different products. Meanwhile, if you add a common Lewis acid in this AlCl3, at room temperature, the reaction only takes 3 hours, and it becomes pretty much selective for the 1,4 cycloaddict. The reaction is catalyzed by this Lewis acid, and it's also more regioselective. So we really wanted to understand what's going on here. So we dug into the literature, and every textbook would say that a Lewis acid, it speeds up the reaction because it lowers the LUMO of the dienophile to which it is coordinated. Why is that important? Well, the key normal electron demand interaction occurs between the HOMO of your diene donating electron density into the LUMO of your dienophile. And you can imagine if you have a lower LUMO, that normal electron demand becomes easier, right? Okay, well, we wanted to study that a bit more systematically and in more detail. So we carried out a computational study where we studied various Lewis acids, all coordinated to an archetypal dienophile. And then we studied the reaction to form the 1,3 and the 1,4 regioisomer. The first step is to investigate the interaction between the Lewis acid and your dienophile. So that's what this scheme shows you. And yeah, you can see the computed interaction energy here using our EDA method for the different Lewis acids. The interaction energy becomes more stabilizing. It becomes more negative on going down this series here. And that nicely corresponds with the experimentally measured relative Lewis acidity here. So a larger number here indicates a more Lewis acidic species. And that is also, if you've run these reactions, you know that AlCl3 is a very strong Lewis acid and iodine is a weaker Lewis acid. So why does the interaction energy become more stabilizing? Well, due to a large part, due to more stabilizing electrostatic interactions. We see that the Pauli repulsion actually becomes larger down the series, and that counteracts the trend. And we also see that the orbital interactions are very significant. There's a significant covalent part of this interaction energy between the Lewis acid and the dienophile. We also see that there is it's not very systematic. So this is the energy of the lowest unoccupied molecular orbital of your complex. And so it's not very systematic, and we would expect this to be the lowest, and it is. We would expect this to be the highest, and it is, but in between it goes up and down. So already that kind of clued us in that the LUMO energy is maybe not so important. Oops. I think my PowerPoint has crashed, so I'm just going to open that up once more. So can someone confirm that they can see my slides again? I'm sorry for the technical problem.
Hamlin,
Yes.
We're watching. That's perfect.
Okay, beautiful. Sorry about that, everyone. Okay, so then let's get into the reactivity, because that's the fun part. So I'm only going to show the uncatalyzed reaction and then the reaction catalyzed by the strongest Lewis acid. And here you see the potential energy surface, or delta E. For the uncatalyzed reaction, it has a higher activation barrier than the catalyzed reaction. And I want to point out that the reaction coordinate that we're projecting the energy values on is basically the difference is, the distance between the shorter carbon-carbon bond that's formed in the Diels-Alder reaction. Okay, so you see that the catalyzed reaction is faster. So why is that? So we then compute the strain energy, and we see that the catalyzed reaction has a less destabilizing strain. So that is a very important contributor to the lower barrier. So why is that so? So here you see the transition state for the uncatalyzed reaction. You see it's a concerted asynchronous process whereby the newly forming carbon-carbon bonds are not the same distance. You can see the delta R, so the difference in newly forming bond length is almost a half an angstrom. When you coordinate your Lewis acid, it induces a higher degree of asynchronicity, so the reaction becomes more asynchronous. And you see that here, so the difference in newly forming bond lengths is now almost 0.8 angstrom. So that leads to a lower strain energy because the terminal carbons are less deformed, they're less pyramidalized. Remember, originally they were sp2 hybridized, and so were these carbons, and now, yeah, they're pyramidalizing, they're becoming more pyramidal. So the degree of asynchronicity has a profound effect on the strain, and we really dove into the origin of this asynchronicity in a very recent publication in PCCP. So I suggest you check that out if you're interested. But by and large, the more important contributor to the faster reaction of the red curve is the more stabilizing interaction energy. You can see it's more stabilizing over the entire reaction coordinate. That prompted us to carry out our energy decomposition analysis. So this is the same interaction energy, only projected on a different y-axis. It's the same data as shown here. So then we decompose that into the orbital interactions. And quite surprisingly, there's very small differences in the curves. So textbooks would say that the red reaction's faster because it has a more stabilizing orbital interaction. And so we were quite surprised by this. Then we decompose it into the electrostatic curve. And that indeed is just the opposite. So the uncatalyzed reaction has a more stabilizing LSTAT. So that's not contributing to the faster reactivity. But in the end, it was the polyrepulsion. So the less destabilizing polyrepulsion for the red reaction leads to a more stabilizing interaction and thus a lower barrier. So that was a very, very interesting finding, very surprising. And so we wanted to understand the origin of the polyrepulsion. For that, we had to look into the overlap of filled orbitals. So the key orbitals that were important were the HOMO -1 on the diene and the pi molecular orbital of the dienophile. And we see that the overlap here is largest for the uncatalyzed reaction and is very greatly reduced upon coordination of your AlCl3. So it becomes, it overlaps less, so there's less polyrepulsion. So here you have the structure, the schematic frontier molecular orbitals, and then the DFT computed FMOs. So what I want to have you focus on is the size of the pi molecular orbital here. So this is the uncatalyzed substrate, very large amplitude here. And this is the carbon, these are the carbons that are involved in the reaction. When you coordinate your Lewis acid, you see that the orbital gets much smaller. So it overlaps less with the HOMO -1 of your diene. So then we want to understand the orbital interactions. Why were they not contributing to the faster reactivity of the Lewis acid catalyzed reaction? Well, the textbooks are right in the sense that when you add a Lewis acid, it does lower the HOMO-LUMO gap, right? The uncatalyzed normal electron demand HOMO-LUMO gap is 2.3 electron volts. The catalyzed one is only 0.7. So that's good. However, that goes with the a loss of favorable orbital overlap between the HOMO-LUMO. So they kind of cancel out there. You also have the inverse electron demand. So now the HOMO, the pi HOMO of your dienophile interacting with the LUMO of the diene. that actually, there's a larger gap for the catalyzed reaction. Larger is bad. There's also a worse orbital overlap. So that's also bad. So the important thing is that the coordination with Lewis acid lowers all of the molecular orbitals. It lowers the LUMO, it lowers the HOMO. So it makes one better and one worse. That's why the orbital interactions are really the same for the uncatalyzed and the AlCl3 case. So the take-home message is Lewis acid catalysis goes via the novel poly-lowering catalysis mechanism. It's not caused by an effective enhancement of Lewis acidity of the dienophile, but instead due to polarization of the pi system away from the incoming diene. So it's the reduction of the 4-electron polyrepulsion with the diene. It's a lower polyrepulsion, which stabilizes the overall diene-dienophile interaction, more interaction. That leads to the lower barrier. The next reaction we'll study is this Michael addition reaction. And this is also carried out in collaboration with these two guys here. And so now the Michael addition reaction looks like this. So the studied reaction involves a nucleophilic attack of the pyrrolidine on the beta carbon of this alpha beta unsaturated methyl acrylate. So it's a 1,4 conjugate addition. And then you form this Vitter ionic intermediate, which is then quenched during the workup. So here's the mechanism. Your lone pair attacks the beta carbon, you get rearrangement of the pi system, and then you form this alkoxide here. Again, looking into applications of Michael additions in functionalizing materials, well, you have this AZA Michael addition here to form this product, which then can undergo polymerization. So you form a very nice, highly organized polymers here. The Michael addition has also been used to functionalize gold nanoparticles. So here's the Michael addition here. This is the 1,4 conjugate addition there. And then also here you have an oxy Michael addition. So under Lewis acid catalysis and 95 degrees, you can control the oligomerization. So you can form dimers or trimers or longer oligomers of these highly fluorinated polymers. More recently, I was interested in studying the iodine catalyzed Michael addition. So we dug into the literature, we found a few examples, and we were kind of amazed by the fact that iodine, right? Nice and cheap, it's a solid, easy to work with, really mild conditions. It can catalyze this reaction that typically needs high temperatures or really aggressive Lewis acids. And so we wanted to study like the most simple archetypal reaction, and that's the one that I've already showed you before. So between pyrrolidine and then this alpha beta unsaturated methyl ester. So that's what we did. We dug into the literature. We found that the uncatalyzed reaction has a barrier of 18.3 kcal. And when you coordinate iodine again to the oxygen of your alpha beta unsaturated methyl ester, it lowers the barrier a lot. It lowers it by 5 kcal per mole. That's a profound rate enhancement. And that nicely correlates with experiment. So this uncatalyzed reaction is very, very sluggish. It only gets to 60% after 15 hours. When you simply throw in iodine, it becomes very fast. You get almost quantitative yield after only 15 minutes. So we wanted to understand the origin of this iodine catalysis. And so the typical explanation relies on this sort of non-covalent interaction between the iodine and your substrate. So Julia yesterday nicely told us about these non-covalent interactions. It's a nice global descriptor to kind of assess the interactions, stabilizing and destabilizing ones in your molecule. And then most of you have probably heard of the sigma hole model, whereby you have this region of positive charge on your halogen, and that can coordinate. This is the positive region on your dihalogen, and that can coordinate to the electron-rich oxygen of your substrate. However, fluorine F2 also has a so-called sigma hole here, and this really just provides a qualitative agreement. So the sigma hole on fluorine is much smaller than on iodine, and then that also agrees with the computed reactivity. So the reaction becomes highly catalyzed from going from none to F2 to Cl2 to Br2 to I2. Again, we wanted to analyze the interaction between our fragments, and so our two fragments would be our X2 and the substrate, and we see that the interaction energy becomes more stabilizing from F2 to Cl2 to Br2 to I2. So this is in line with the increasing Lewis acidity of your dihalogens. Why is that? Well, it's not because of the polyrepulsion, because that becomes more destabilizing. It counteracts the trend, but it becomes more stabilizing because of enhanced electrostatics. This number becomes more negative, becomes more stabilizing, and that makes sense because halogen bonding is mainly an electrostatic phenomenon. However, I also want to point out there's still a significant covalent part, and that's really important. I'll describe that later on. So this becomes more stabilizing, and that contributes to a large degree the stabilization of the interaction. Again, we're going to get into the reactions, and I again focus on the uncatalyzed and then the iodine, which is the fastest Lewis acid in this case. So you see that the iodine catalyzed reaction, this is the transition state with the dots. Indeed, it has a lower activation barrier, so it's a faster reaction. So now we plot our strain energy. We see that the curves are basically superimposed, so the strain doesn't play a very big role in explaining the lower barrier for the red reaction. Instead, it's the more stabilizing interaction energy. So the more stabilizing interaction pulls the barrier down for the red reaction and leads to a faster reaction. This is the same interaction curve, again plotted on a different axis. I should mention here that the reaction coordinate is the distance between the nitrogen of the pyrrolidine and the carbon, the beta carbon on your alpha beta unsaturated methyl ester. Okay, so now we want to understand, why is the red curve more stabilizing? Well, it's not because the orbital interactions. They're superimposed. They play no role here. Here's the electrostatic interactions. They display the opposite. And the PowerPoint crashed again. Sorry about that. I'll quickly get back to where we left off. I apologize for that. So yeah, the electrostatic interactions are actually opposite the trend. So they actually play the opposite role. So why is the interaction energy more stabilizing for red? Again, it's the polyrepulsion. We were very surprised about this. This is now the second example of this poly lowering catalysis. So we were really amazed by this. So it's traced back to the repulsion between your fragments, and that is really amazing. So here we wanted to understand the trend in the poly, again we looked at the overlap of filled orbitals. So in this case, the key orbital overlap was between the lone pair on your pyrrolidine on the nitrogen, and then the pi system of your acceptor, your Michael acceptor here. So the overlap of these orbitals in the uncatalyzed case is 0.17. In the case of the iodine catalyzed reaction, it decreases to 0.1. So the overlap is largest and most destabilizing for the uncatalyzed reaction, and it's the smallest, least destabilizing for the iodine reaction. So we really wanted to understand what is the origin of that, and I want you to kind of look at the p orbital on the carbon, on the beta carbon here. So here we've coordinated fluorine, F2, and here we've coordinated I2. You see that the p orbital is very large in the case of F2 and very small in the case of I2. And why is that so? We traced it back indeed to the energy of the sigma star of the dihalogen. So the sigma star for I2 is very low lying compared to the LUMO of F2. And that has a very profound impact on this, because upon coordination with your substrate, you're going to get a flow of electrons from the substrate, from the Michael acceptor, to the to your dihalogen. So the lower that LUMO is, the better the charge transfer. So that really polarizes the pi molecular orbital away from the CC double bond. And that polarization leads to less overlap with the nucleophile, with the lone pair on your pyrrolidine, as it attacks this carbon. So really, really amazing. So now we wanted to understand why the orbital interactions are playing a less important role. Well, as one would expect, the key charge transfer event occurs between the lone pair on your nucleophile and the pi star of your Michael acceptor. So the uncatalyzed reaction has a HOMO-LUMO gap of 6.1 electron volts and an overlap of 0.19. And the iodine case, indeed, as the textbooks would say, it goes with a lower HOMO-LUMO gap, right? But they don't say anything about the orbital overlap, which actually becomes worse. So they offset each other, they cancel out. So it leads to an identical orbital interaction along the reaction coordinate. So the orbital interactions are not important for Lewis acid catalyzed reactions. That's what we're finding. So these conclusions are very similar to what we've seen before. So the dihalogen catalysis goes again via this poly-lowering catalysis. It's not due to an enhancement of the Lewis acidity of the Michael acceptor, but due to the polarization of the pi system away from the CC double bond. That reduces the polyrepulsion. Just going to open that up again because this crashed again. Here we are. I apologize for that. So yeah, the concept of this poly-lowering catalysis is actually very, very broad, and we've been very fortunate to have found and studied various reactions. So here you have the Michael addition. Here you have the Diels-Alder reaction. We've looked at aromatic Diels-Alder reactions. We've looked at bifunctional hydrogen bond catalysts. These just, we just saw the Nobel Prize in chemistry this year was awarded to Macmillan and List, and they were the ones that developed these catalysts. We looked at epoxide ring openings, other pnictogen, chalcogen, halogen bond catalyzed Diels-Alder reactions. We looked at ene reactions and also these aza heteroaromatic Diels-Alder reactions. All of these go by the poly-lowering catalysis. Very, very broad and general framework that we uncovered just by applying our methodology. And the last class of reactions I want to talk about are 1,3 dipolar cycloadditions of cycloalkynes. This was carried out in collaboration with Professor Bickelhaupt and Professor Hauk at UCLA. And the 1,3 dipolar cycloaddition is a reaction between a 1,3 dipole and an alkyne in this case, and they react and they form this triazole cycloadduct. And again, this is a paracyclic reaction. The electrons are migrating in a cyclic fashion here. And we were interested in what happens when you strain your alkyne. So we dug into the literature and we found when you have this phenyl azide reacting with a linear alkyne, requires heating to 120 degrees for 1 day to afford 72% of your triazole cycloadduct. By simply straining the alkyne, moving to the cyclooctane, reacting with the same azide, it reacts 20 degrees less than 5 minutes to give 73% yield of your triazole. So bending or straining your alkyne has a profound effect on the reactivity. And not only that, but the ring size is very important. So here you have the second order rate constants for these 1,3 dipolar cycloadditions with an 8-membered ring and a 9-membered ring. You see that the less strained 9-membered ring reacts 2 orders of magnitude slower than the 8-membered ring. So smaller rings are faster than larger rings. And these strain-promoted azide-alkyne cycloadditions have been used to functionalize polymers. You can get highly decorated polymers. They can functionalize the surfaces of these quantum dots and stabilize them. And you can also generate polymers and then use these Spock reactions to cross-link them and arrive at very stable polymers that are highly decorated. Very cool. And so typically you're going to try to functionalize these cycloalkynes and you're going to try to build in as much strain as possible. So typically how that's done is by increasing the number of sp2 hybridized carbons in your cyclooctane. So this is the first generation, the cyclooctane here. And then you add more sp2 hybridized carbons. And then you get to this Barak version that has all sp, except your alkyne, it has all sp2 hybridized atoms. Except this is so unhappy that it actually rips itself apart. It degrades really, really fast. So what we were looking for is another tuning handle to increase the reactivity of these alkynes without compromising the stability of the reagents. There's also been 2 examples of other rings, 7-membered rings and 9-membered rings. So here you have the optimized geometries of your methyl azide, your cycloheptine, octine, nonine, and then your linear 2-butane. And just to recap, so you see that the internal angle of the alkyne is smallest and most strained in the case of the 7-membered ring, and it's larger and larger, and of course it's 180 degrees when there's no influence of your ring. So typically, if you ask experimentalists, why are the smaller rings faster? Well, they say they're pre-distorted and they're highly strained, and then they react really, really fast. They also maybe invoke the concept of strain release. But you can imagine that this is highly strained, and so is this. It's still strained. And when you have no distortion, it has a really slow reaction. So we again applied our methodology. Here's the activation barriers. Here's your linear system, has the highest barrier. When you move to the 9-member ring, the barrier goes down. The reaction becomes faster. Here's your 8-member ring, even faster. And then your 7-member ring, even faster. This is the fastest reaction we have so far. Here are the strain energies. And this is actually really amazing because the strain for the linear system is most destabilizing. But the strain for the cycloalkynes are all the same. They're the same. All the curves are overlapped. So the strain energy does not contribute to the faster reactivity of these cycloalkynes. That was really amazing. Instead, why are the smaller rings faster? Well, they have a more stabilizing interaction energy. This more stabilizing interaction pulls the barrier down and to the left to an earlier point. And this reaction coordinate is the distance between the carbon of your alkyne and the nitrogen of your azide. So when we decompose the interaction energy using our eta, again, this is the same data plotted on a different axis. We see that the polyrepulsion doesn't contribute to the trend. It's overlapped. We see the orbital interactions. There's some variation. And the L-stat is also overlapped, not very important at all. But this is amazing. So you can recover the trend in interaction by solely looking at the orbital interactions. Those are most stabilizing for the 7-member ring, the blue, and then it goes green and then red and black. Same thing for the interaction. So the orbital interactions for these reactions are very important. So we wanted to understand why that is so. So then we did our analysis of the frontier molecular orbitals, and we looked at the normal electron demand between the HOMO of your methyl azide and the pi LUMO of the alkyne. Well, we see that the smallest rings have the smallest energy gap. That's very good. Smaller gap is better, and it has the largest overlap. As the ring size increases from cycloheptine to octine to nonine to 2-butyne, the energy gap gets larger. That's bad. And the orbital overlap gets smaller. That's also bad. So both of these effects contribute to weaker orbital interactions. And the same can be said for the inverse electron demand. So now we're looking at the donation of electrons from the HOMO of the cycloalkyne to the LUMO of your methyl azide. And you see again, for the smallest ring, it has the smallest HOMO-LUMO gap and the largest orbital overlap. So we wanted to understand, why does bending affect the frontier molecular orbitals? So we plotted we analyzed the energy of the orbitals as a function of CCH bond angle. So on the left, you have your linear acetylene, and here's your LUMO, and here's your HOMO. And you see, as it bends from 180 to 150 to 120, the LUMO goes down, becomes stabilized, and the pi HOMO goes up a little bit. And that leads to a smaller, inverse electron demand and normal electron demand interaction. So the smaller rings lead to more favorable orbital interactions due to this. This is the mechanism for the different energy gaps. And we can understand why that is so. So here's the linear pi HOMO. Upon bending, you have an out-of-phase admixture of the 1s orbitals on your hydrogen with the carbon 2p orbitals, and that destabilizes the pi HOMO and the pi star. Upon bending, you have an in-phase admixture now. This is the bonding molecular orbital combination to form the pi LUMO, and then so you have a nice stabilization. It should also be pointed out that bending of the alkyne also polarizes the orbital on the external face of the alkyne. So here you have the HOMO and the LUMO of 2-butyne. You see that they're of the same magnitude. However, when you bend it, here's now cycloheptine. You see now the HOMO is much larger on the external pi face, and that's where the azide reacts. So bending it polarizes the orbitals away, and then it can overlap to a greater degree with the azide. So pre-distortion enhances the reactivity of cycloalkynes, not only by a reduced strain energy, and what we found, this is the most interesting thing, but also by a smaller HOMO-LUMO gap and an enhanced HOMO-LUMO orbital overlap. So very important to look at both of these parameters here. And the most important thing of our paper was that by tuning the orbital interactions, you now have a novel mechanism for increasing the reactivity, and you don't have to solely rely on increasing the strain energy of the alkyne. And so our findings are already being used by others to tailor design novel strain-promoted azide-alkyne cycloadditions. And I just want to mention that all of you can do the same exact analysis that I'm doing. So we publish a step-by-step instructional guide. It's basically like a cookbook that says, first step, do this, second step, do that. So it's a really, really clear step-by-step guide. We publish this in Nature Protocols on how to do the activation strain and the EDA analysis. If you want copies or reprints of any of these papers that I've talked about, just simply email me. I'm happy to send them. I'll send you a PDF. We also have a brand new review on these reactions published in ChemCom, and all this analysis was carried out using PyFrag. This is an open source software. You can download it on GitHub, and you can tinker with the source code and do it all yourself. And this almost made it. Here we are. Yeah, and PyFrag, we recently published that work in the Journal of Computational Chemistry, and we made the interface compatible with ADF, Gaussian, and Orca turbomole for the activation strain analysis, and then the energy decomposition analysis has to be done with ADF. And with that, I want to thank the group and the funding agencies to allow me to do all the research with our outstanding group here in Amsterdam. So here you have Matthias Bukkelhaupt, here you have Professor Celia Fonseca-Guerra, and myself. And we together lead the Theochem group. We're based at the FU. NWO gives us funding. SCM develops the ADF code, which we use for all the DFT calculations, and then we run all of our calculations at the Dutch National Supercomputer Organizer, SurfSara. And now I'm happy to answer any questions that have.
Professor Hamlin, thank you so much for your outstanding talk. It was very explanative. Thank you so much. We have a lot of compliments here in the chat and a flooding of questions. We'll try to address all of them. Well, let's start with Professor José Valquimar de Mesquita Carneiro. He asks, one fundamental point is the definition of the reaction coordinate. Even if the two reactions are similar, the atom-atom distance in one of them does not necessarily correspond to the same distance in the other reaction. The point is how to define a generic reaction coordinate.
Yeah, that is a very excellent question, and I think I can illustrate that point here. So in this case, this is the Michael, I believe this is the Michael addition reaction. So our reaction coordinate was, say, sorry, let me go back to here. So our reaction coordinate was the distance between the nitrogen and the beta carbon here. Indeed, when you have coordination of the different Lewis acids, or in this case, the dihalogens, that distance is not the same. And that is why the transition states occur at different points on the reaction coordinate. So here you see that the catalyzed reaction is earlier and the uncatalyzed one is later. So what I would suggest is that you pick a bunch of reaction coordinates. So this is only one of them. We also tried, say, the elongation of your carbon-carbon double bond. right? Because over the course of the reaction, it goes from being a double bond to a single bond. We did the same analysis with that different reaction coordinate, and you got the same conclusions. And this varies based on the reaction. So I would say test it out on a bunch of reaction coordinates and check that the conclusions are unchanged.
All right. But let me add something to this question of Professor Alkmaar. What if we are analyzing a Diels-Alder reaction in which we have a lot of a lot of reaction coordinates that are being changed along the reaction?
Yeah. So this is one of the Diels-Alder reactions. Yeah. So in this case, what we do is we look at the shorter newly forming carbon-carbon bond. That's one reaction coordinate that is intimately tied to the extent of the reaction. That's another key thing. You need your reaction coordinate to be a very good descriptor of how far along the reaction has gone, right? So if we have a very long bond, we know, yeah, the reaction hasn't really occurred yet. They're just beginning to interact. And we know if we have a very short bond, then we're near the product. We've also done the reaction coordinate where you project these energy terms, which are derived from the IRC, on the elongation of the double bond. So in this case, in the reactants, it's a double bond. In the products, it's a single bond. We also did it on the sum of the distances of the two pi bonds in your diene. You can imagine over the course of the reaction, they go from a double bond to a single bond. Yeah, the options are endless. You can project these terms on any number of reaction coordinates, but the important thing is that the reaction coordinate is a very good descriptor of the extent of the reaction.
Mm-hmm. So you need to evaluate all the possibilities to see what's.
Yeah, the first thing is to identify all possible reaction coordinates, project your energies on them, and then come up with the one, and then see if your findings are robust. You know,
Okay.
do you have the same conclusions, or is something changing, and why is it changing? Luckily, in this case of the Diels-Alder reaction, all of these projections all explain, they all give the same conclusion that it's Pauli lowering catalysis in every single case. And you can find all this data in the supporting information of the papers, I believe.
All right. The next question is from Karini de Andrade. She asks, the choice of the fragments has a great influence on the analysis. Can the wrong choice for large systems impair the understanding of the reaction mechanism?
Yeah, that's a very good question. Thank you. Yeah, so in the framework of the activation strain and in the framework of the ETA, you have to choose fragments, right? And that is a very good strength of the methodology, because you can choose different fragments of the same reaction and check how that influences the factors controlling the reactivity. Well, in this case, it's very easy to pick your fragments, right? Because you have a bimolecular reaction of a diene interacting with a dienophile. That's very easy. We have our two fragments, 1 and 2. The same is said with the Cycloaddition, and the same is said for the Spock reactions that we investigated. It becomes a bit more difficult when analyzing intramolecular reactions, whereby it's a unimolecular process. And we have ways to do that, of course. I'm happy to discuss the technical issues. We explain how to do that already in the Nature Protocol paper. Yeah, so then you have to cut a bond, you split it homolytically, and then you can basically subtract out the energy of forming that bond. But yeah, you have to take care into selecting your fragments. That's absolutely true.
Mm-hmm. What about you? you told about bimolecular and unimolecular. What about supermolecular environments? Like, let me be specific. What if we are considering a cluster of water molecules or water or solvent?
Yeah, typically you would like to group, say the solvent molecules it is easiest when you have two fragments. I'll be honest. So you want to try out different groupings of your fragmentation and see which one gives you the most chemical insight, I would say. And I think this topic has been nicely discussed recently in theoretical chemical accounts by the group of Miguel Solá and Jordi Porter. And they looked at, indeed, water clusters and the choice of fragmentation and yeah, depending on your choice of fragmentation, it can give rise to different results.
Right.
But that is, in principle, that is a strength of the method, because you can check how your choice of fragmentation influences the different chemical properties of the, say, for water, the different dissociation or interaction patterns of your water clusters.
All right. We have some more questions. I believe I'll pick up two more. Professor Luciano Costa asked, Professor Trevor, can we say that the strain energy is the difference of the relaxed fragments and the interaction energy, like the non-relaxate? If so, is this also included into the electrostatic interaction?
So thank you for the question. I think we can see that maybe from this slide. So the strain energy would be the energy difference between the distorted fragments. So picture at any point on the reaction coordinate, but in this example at the transition state. So this is the transition state for the Diels-Alder reaction. I can compute the strain energy by the energy difference between the distorted 1,3-butadiene, take the energy of that, minus the energy of the optimized fragment. This is the optimized S-cis 1,3-butadiene. And we know that as it reacts, the energy goes up, right? It's in a non-equilibrium structure. It's now in the transition state. And the same thing for the ethylene fragment. You get the strain of the ethylene fragment by the energy difference between this, the distorted fragment, minus the optimized fragment. The sum of the two distorted fragments give rise to the total strain energy in the transition state. Yeah. Did that answer the question, I hope?
I believe so. He asked about if the term includes the electrostatic interaction.
Yeah, so it does not include any interaction. It's solely the energetic penalty for deforming your reactants.
Yeah. That is why it is also called interaction distortion. Right?
Yeah, indeed. Yeah, so this analysis is classically called the distortion interaction model. Yeah, because you're doing this analysis at the transition state. Yeah.
Very nice. And our last question is from Maicon de la Merlina. He says, Dear Professor Hamlin, thank you for the great talk. Your group recently defined the term Pauli-lowering catalysis. I was wondering if the catalysis involved in such mechanism must have acid character, or we could think of the other chemical properties with similar effects.
I heard something about acid character. Would then that be, would that relate back to, say, like the electrophilicity of the reagents or something like that?
Well, I'll read again. I was wondering if the catalysis involved in such mechanism must have acid character, or we could think of other chemical properties with similar effects. All right. I believe that he wants to understand if the Pauli lowering catalysis needs to have anything or a close relationship with acid catalysis, since we are lowering the repulsion between two uh, uh, orbital with electron pairs.
So acid catalysis. So like maybe like this example where this is like a Bronsted. This is a Bronsted base. So yeah, if you protonate something, then that also, I think in this case it also leads to, so here we looked at monoprotonated diene reacting with an alkene, and if you protonate the nitrogens, then it also enhances the reactivity. So this is acid catalysis.
But I believe he also considered Lewis acid catalysis, like all types of acid catalysis.
All types of acid, yeah. So far we've shown that we've mainly studied Lewis acid catalyzed reactions. In this case, we also studied metals. So here we have alkali metals. So we looked at cesium, rubidium, potassium, sodium, lithium, and they also act as, say, Lewis acids. It's all about pulling electron density out of the reagents and enhancing the reactivity. We're going to start getting into Lewis base catalysis, Bronsted acid, Bronsted base catalysis. So this is a pretty general phenomenon. It's not only for Lewis acids.
Right. Thank you so much. There is one last question about if the PyFrag is free. Can you talk about?
Yeah, PyFrag is free. It's open source. So this is our postdoc here, Chabot, and I really pushed him to make this software easy to install and easy to use. So we have nice documentation, and it's basically like click and download, and it installs on your Linux machine. It's free. I want you all to use it if you can. Check out this JCC paper and then the Nature protocol for how to do it. But it's open and free. And feel free to reach out if you have questions.
Right. Well, Professor Hamlin, thank you so much again for the amazing explanations. We are very happy to have you here with us. And well, thank you.
Thank you very much for inviting me and for moderating the session. And thank you all for the participants. Great questions, and it was lovely to be here.
That's nice. We are now closing the morning section, and we'll be back at 2 p.m. o'clock in Brazil time. I'll see you later. Bye-bye.
Okay, thank you. Bye.